Good afternoon, everyone. Welcome. Thanks for joining this week's GMU Center for Satellite Neuroscience Research weekly webinar. We do have an exciting talk today on AI and air quality modeling. And we have our Associate Director for Research here, Dr. B.H. Bach, and he is going to host and introduce our speaker today. So take it away, B.H.
All right. Hi, everyone. I think most of you are here. I think some of, few of our folks soon to join. And Daniel, our director, is also here. My name is BH Bag, as you all know. Today I'm going to introduce you one of the young scientists who is working on air quality and air, AI study, combining. It's an exciting study she's doing. Let me just briefly introduce her to you guys and then let her start her seminar. So Dr. Seohui Park is on her PhD in environmental science and engineering from one of the prestigious university in Korea called UNIST. And she's been focusing on a studying about estimating ground level particulate matter using satellite remote sensing and numerical modeling work. And also she worked on developing a level 4 GEM surface air quality algorithm for PM2.5, PM10, ozone, and NO2 through machine learning integration of the satellite and model output and ground observation data for near real-time retrieval across the East Asia. Since 2023, she joined the NASA Goddard Space Flight Center through Morgan University as a postdoc researcher. She's been continuing her work of the machine learning integration of the multi-sensor satellite like Tempo and GOES-R and combined with the model simulation as well as the ground measurement data to estimate the surface PM2.5. She also developed the automated pipeline for the near real time of the PM2.5 mapping. So her research is interested in the machine learning integration of these measurement data satellites and air quality modeling and observation data to improve the understanding of the atmospheric composition and pollution dynamics. So here we go, Dr. Park, floor is yours.
Hello, thank you, BS, introducing me and also for inviting me to speak today here. So it is really pleasure to have opportunity to share my work with you. So today I'm gonna talk about enhancing the air quality monitoring with AI and multi-source observations. Okay. Yes, maybe you guys already know about the problem of the air quality. So the recent years, many countries have implemented different policy and action to improve air quality. But even with this effort, air pollution is still a major concern in many areas. So that's why it is very important to keep monitoring air quality on a regular basis. So we can do this in several ways, like ground observation, satellite remote sensing, and model simulation. Ground observation are usually point-based measurements that represent the truth value of surface air quality. The most countries operate national monitoring network to measure and management the pollutant like PM2.5 and ozone. But because these stations are sparsely distributed, they cannot fully capture the air quality conditions in area without the monitoring site. And the remote sensing provide aerosol information with high spatial and temporal resolution over the large area. To estimate surface PM, we usually use the satellite-based product like AOD, aerosol optical dips. And recently, some studies have started to use the level 1B data, such as radiance or reflectance, directly to estimating surface PM concentrations. And with geostationary satellite, we can now monitor the atmosphere continuously throughout the day rather than getting just one or two snapshot, the image from the polar reading satellite. And also, the model simulation can give us the continuous spatial information about air quality, something we cannot get from the ground observation. They are powerful tool for studying pollutant transport and chemistry, but they are also computationally expensive and take a lot of time to learn, which make them difficult to use for real-time monitoring and forecasting. So in my study, I mainly use multi-source data related to the air quality. So these include ground measurement and satellite remote sensing and model-based meteorological data. The main satellite data I use are the aerosol and trace gas products such as AOD and NO2 and ozone total column product, mostly from geostationary satellite like GEMS and GOES-R, and I recently used the radiance from the tempo data. And also the meteorological variables such as wind speed, temperature, boundary height are also very important to improve the model performance. So to bring these all data together, I applied the data fusion technique, which involves spatial and temporal matching before training the AI model. Then I applied the machine learning or deep learning method to build the PM2.5 or the other trash gas model that can estimating surface level concentrations. And yeah, but there are various type of AI model, including tree-based, machine learning, or like one-dimensional neural network, or for the one-dimensional neural network for tabular data set, and also two-dimensional image-based training network, such as convolutional network or UNet model. So in short, my work focused on integrating multi-source data through AI to better understand and predict the surface air quality monitoring. The core idea of my study is data fusion. So as I mentioned, the ground-based monitoring gives us accurate PM measurement, but only in the limited location. And satellite cover large area, but they only provide atmospheric total column informations, which is not reflected at the surface level. So I use the machine learning approaches to bridge this gap. The model learns the relationship between satellite data and ground measurement, where both are available, and then they apply this relationship to the other area. So the goal is to combine the strengths of both data source, the broad coverage and accuracy, to produce the hourly surface level PM2.5 estimate. So far, I've talked about how different data set and AI model are used to estimating surface air quality, but one important thing remains: how can we understand what the AI model has actually learned? So this is where explainable AI, called XAI. So in my work, I use the sharp value. The sharp, which stands for sharply additive explanations, help us understand how each input variable contributes to model's prediction. It assigns the numerical value, called sharp value, to every feature, showing whether it increased or decreased the predicted result. For example, in this diagram, you can find the input data here. So the AI model has multiple input, and then running using the AI model using these input variables such as radiance or temperature or AOD or something like that. And then sharp then break down into model's prediction into contribution of each of these input. The red indicates the higher feature value and blue indicates the lower value, showing the whether each variable increase or decrease the prediction. And the horizontal position shows the direction and magnitude to their influence on the model prediction. In short, the sharp help us understand why the model made a certain prediction. It provides both direction and magnitude of each variable's impact on the result. Yeah, here's GEMS level for estimated surface air pollutant concentration. So my work, they adopted my work like real-time learning, which only considering the last 30 days samples, not all the historical samples. The manual research, which adapted AI model, they used the historical samples such as at least 1 or 2 years. They collected together and then learning with the historical samples. But the air quality is very, very dynamic and they change every hour and every day. So it's very hard to estimating using the whole historical samples to estimating now their pattern. So I adopted this concept to estimating more accurate surface PM 2.5 concentration and 10 or other gas species. So I bring my paper here. So I just briefly introduce the real-time learning part here. So in this paper, I suggest 3 schemes because the for the PM 2.5 surface to estimate surface PM 2.5 is very affecting like concentration and time. So in this paper, we applied PM concentration weighting and time weighting samples to here. And the final version, the scheme 3, is adapted for the GEMS level 2 data. So the model performance is very depending on the range and distribution of the training samples. So for, as I mentioned in the previous slide, for the air quality data is very dynamic and very depending on their samples. So, but also their sample is very unbalanced. So usually the low concentration observed the most of time and high concentration is very rare in their data set. So to address this issue, I applied the PM concentration weighted sampling, which combines both oversampling and subsampling. In the oversampling process, high concentration samples, which are really, really rare in the data set, are increased in generating additional samples. So we created these additional high concentration samples to make a balance within the data set. So I give some 5% perturbation for the neighboring pixel with the high concentration point. And the second approach is time-weighted sampling, give us more importance to recent data compared to older data. So in practice, this means removing the oldest samples and assigning higher weight to the latest observations. After providing this weighting process, the training samples are accumulated within the 30 days. So with 1 hour moving window like this process. So we remove the past samples and we get the new recent data set and then make a new model for every hour and then generate the surface PM 2.5. This is for the results. So the red box is scheme 3 shows a better performance than scheme 1 and 2. So that's why we adopted this scheme for the GEMS level 4. So you can find these here. The combined version is better performance in this study. So we've checked these performance by different time scale. This is for the by UTC scale. So you can find the yellow line is for the scheme 3, but the scheme 3 resulted in the smallest error for the all operation time, 0 to 7 UTC. This means that concentration weighting contributes more than time weighting to improving the performance of the real-time running model. In particular, for error at 0 UTC here was the highest, showing the decreasing pattern from like here, decreasing pattern with increasing time for the 7 UTC. So that means the more information are corrected in the same day, the higher the accuracy. This is by the month scale. So during the month, the higher model error shows the summer season. This data set contains a large number of low concentration samples compared to the other concentration level. Also, the total number of the samples during these months, the summer season, shows have the smaller than other period, like here. You can find the moderate and high sample is mostly smaller than other season. So, okay. So in contrast, during the winter season, from October to February, there are more samples with a moderate and high PM concentration. So, so because of this, they have larger standard deviation, but they show better performance than the summer season. Yeah, this is a comparison between real-time learning and offline model. The offline model means like usually the previous study usually adopted the whole the historical model. In this study, we used the 4-year samples. So offline model using the whole 4 years and training using the historical data set, and they get the data later here. And then we compared using the real-time learning model and a real-time learning model for the tenfold cross-validation. They're even better than the offline model validation. And this is for the sharp value for real-time learning model. So as I mentioned, the real-time learning model is conducted for every hour. So that means for the sharp value generated every hour. So we accumulated all the sharp value samples and plotting together in here. So maybe you can just pick their order, the importance order. So in here, both PM10 and PM2.5, the AOD variable is most important factor for these two real-time learning model. And also DOI. DOI means day of year, they represented the seasonality. So especially in the East Asia, they have their seasonality for the particulate matter. So that is the why they have the most important variable here. And this is annual distribution. So yeah, PM10 and PM2.5, they show the decreasing pattern for the past from the 2016 to 2018. But here in the Korea, they shows increasing pattern from the 2018 is very corresponding with the previous study with in the 2018 they have lots of extreme air quality date, so it's very corresponding with previous study, and we also get this trend in our study too. And also we adopted error for the real-time learning model. So we calculated the error for using their distribution. That means each station calculated how many station is included in the center pixel. So we using for the radius for 18 kilometer, that means 3 by 3 pixel size. So we calculate how many station is included in that area, and then we compare their performance together. So you can find here the lower 10% shows very big error in here. Comparing the high 10% station, it shows very less error here. So that means it's very important to, if we have a lot of station together or neighboring together, it shows their surface PM performance is increased together. So now in this paper, we use GOSI, and then after then they adopted, NIER adopted GEMS for this algorithm. So now you can find this distribution PM2.5, PM10, and NO2 in this website. So after that, I using these real-time learning products to combining the CTM model. So in this study, For the WorldCam, we adopted these estimated PM10 and PM2.5, which is from the real-time learning model. And in this study, especially, we separated the station for the validation process. So here, the red dot is calibration station, and blue triangle is 15% for the validation, around the 300 station for the East Asia. So we compared without data simulation and a simulation with AOD from GoC and machine learning simulation with using this real-time learning model based real-time learning model based PM10 and PM2.5. Yeah, these samples using for this process. Yeah, here you can find in the red box is machine learning data simulation shows more accurate with observation comparing the without or with AOD from GoC. You can find the data performance in the scatter plot here, the right panel in the bottom. For the both PM10 and PM2.5 shows highly increased compared the before without and with AOD data simulation. Especially their variance is highly increased in when we using the machine learning as input variable. And also you can find their prediction skills for the first hour. Sorry, for the first hour is extremely high, their performance in here. And also even their past for the 24 hours, almost similar, but they even before the 24 hour, they shows still low error and higher correlation with for the longest hour prediction for both PM10 and PM2.5 too. So this is for the validation samples only for the 15%, which means not including in the real-time running model. So these performance also shows very similar with validation and calibration. They shows very similar pattern. That means the strong prediction skill is showing here when we use applies as input variable with the data simulation. And this is the other paper for the real-time learning model to the CMAC. So Dr. Yu applied our data set to as a input variable for data simulation together with Gaussian AOD and ground observation. So there you can find here the green line is everything together, like Gaussian AOD and our real-time learning model-based PM and ground measurement PM concentration together for the data simulation. They shows our best performance in here, especially in these three high concentration period like Asian dust, aerosols, and long-term transfer here. They are corresponding with the ground observation PM2.5. And for now, I'm conducting the ground level PM2.5 estimation from the geostationary satellite for the USA, especially in the continental USA. So this is for PM2.5. We found which model is most better for this area because their source is quite different from East Asia and the USA. So we applied the several model to estimate surface level, random forest, and right GBM and DNN here. So total performance is the three best model is better than DNN, but the high concentration, the DNA model is strong than the other models. So we adopted DNA for the final model, and then estimating whole the USA here. And this slide shows the bias histogram for DNA model. The green dashed line in here represented plus and minus sigma boundaries. The blue dashed line shows the central 67 range, and red line indicates the outlier boundaries in here, the outline range. The percentage bias is very close to the zero at this minus 0.32%, and the mean bias is minus 0.03 microgram per cubic meter, indicating that the model is nearly unbiased overall. So however, when we look at the positive and negative bias separately, we see that the model tends to slightly underestimate the actual value with negative bias mean of minus 4.14 here. The standard deviation is about 5.33, and about 84% of prediction falling within 1 sigma, indicating that the bias are concentrated in the narrow range. Outlier defines bias based on the interquartile range following the Kentucky method, and about 6.4% of samples are classified as outlier. It's a very small number. So however, the remaining 93.6 of the samples which are not outlier showing good performance, indicating that the model works well for the most samples. The overall, this suggests that the DNA model generalized effectively within the significant overfitting and provide a accurate estimate for the most data point. And also we found this 2023 period, we suffered Canada wildfire. So our model captured these 3 smoke waves from June 7 to 9 and 28 for 30 and July 16 to 18. You can find these estimating PM2.5 distribution with point from air now. So we can show this high concentration in the east part from the Canada in daily scale, and also we can capture high concentration in New York City in east in our hourly scale. So for the time series pattern, we can find these very, very high peak point, because in the USA, the normal PM2.5 condition is very low. That means the under around 40 is usually measurement in the normal condition. So it is very difficult to estimating extremely high concentration without any like very low normal condition. So we can find these first smoke period and then second and third one. And this is for the New York State, and this is for specific station point. They captured very well in here. The orange line is estimating PM2.5, and blue line is observed air now PM2.5. So you can find here around over the 400 microgram per cubic meter. The DNA model can estimate these extreme PM2.5, and also over the 100, they capture it too in the other station too. And also, in this paper, we use the 5 months of the tempo data. The tempo data is available since August 2023. So in this paper, we found when we using the tempo data, their model performance is significantly increased, especially in the high concentration area here. In the Minnesota, you can find in time series here, the green line is estimate PM2.5 is more corresponding with observed air now PM2.5 than estimated PM2.5 without tempo here. So now we extended this study period to the 1 year and then applied for the whole 1 year to estimating PM 2.5 for the USA using the temporal radiance data. And also for the FRP variable is additionally used as input variable because in the USA, the wildfire is main reason to increasing the surface PM 2.5 concentrations. So this is the simple diagram for the study. We using the 1 year data from 2023 August to 2024 July, and then using the several temporal radiance data, and also additionally using the ABI FRP data as input. Here you can find these two comparison scatter plot. The number is not too big different, but you can find in here. So when the FRP is available over, that means over the 0, the performance is extremely increased than without the FRP area. So that means when we adopted FRP and then the AI model learning using their value to estimating PM concentration, and then the performance is getting increased. So this is the model performance by the month. You can find the here green line is without FRP and orange line is with FRP model, and then this shadow is sample count. So in the August, the extreme wildfires occurred in the western part, so the extreme sample is lots of measured in this month comparing the other months. So they shows the higher performance and also shows higher error than other months, but that is because they have the lots of high concentration samples here. So this sample count is only over the 100 microcubic meter. And in here, when this is also sharp value for the DNA model using the temporal radiance and ABI FRP data. So when we look at the variable importance in here, the UV channel like 354 is the highest concentration to model performance. And also for the top 4 most important features are all the temporal data. That means these temporal radiance data is mostly contributed to estimating surface PM 2.5 than when without using the temporal or FRP data. And in here, they act like negative effect for the 354 radiance data to estimating surface level. It is very, that means that as the radius increase, the estimating PM 2.5 is decreasing. So that means the negative effect. So it's the same. These reflect the characteristic absorption behavior of the UV radiance. So I can find these two negative and positive effect for the visible channel here. So this is for seasonal distribution for the PM 2.5 for spring, summer, falls, and winter. So you can find these high concentration, and also the summer season, they have lots of wildfire in the western parts. They can capture this high concentration pattern in the seasonal distribution too. And also I checked some cases for extremely wildfire season here, 2023 August. So the green line is estimating PM 2.5 with FRP is slightly higher than the without FRP data, they can capture this increasing pattern and decrease, and also the next day they can capture the extreme increase, and then the time series pattern were captured with the DNA model. And also the other case is Camp House fire in Minnesota. You can find in the ABI AOD can measure these high, maybe you can find here. And also our model can capture these wildfire case to estimating high PM concentration in the same area. The other case is Jibor fire case this year, August 9. So here you can find the FRP. They can capture the FRP value in wildfire area. The AOD measures the high value, and also our DNA-based PM2.5 can capture this wildfire related PM2.5 concentration. Even this area is very small, like this campfire case and this wildfire case. Even they have their narrow area, our model can capture and estimating the extreme PM2.5 concentration case. And for the summary, the integrating satellite, ground, and model-based data with AI technique improve the accuracy and spatial temporal coverage of surface air quality estimation, and especially the geostationary satellite enable continuous monitoring and supporting the real-time air quality monitoring. And also we can use the AI-based data fusion framework can be used alongside chemical transport model to reduce bias and improve the prediction skill. And for the AI, we can use the explainable AI to provide the interpretability, increasing trust, and usability of AI-based system for estimating ground level PM2.5. This is all I have today. Thank you for listening, and if you have any questions, let me know.